Please subscribe to support the channel. The universe is vast, mysterious, and filled with wonders that challenge even the most imaginative minds. Among its most astonishing phenomena are massive stars, celestial giants so enormous and powerful that they defy everyday human comprehension. These titanic spheres of burning gas are the engines of the cosmos, forging elements in their cores and influencing the evolution of galaxies themselves. While stars like our Sun are already immense by human standards, some stars are so colossal that traditional comparisons almost fail. Their sheer size and energy output stretch the boundaries of what we consider physically possible, and they play a crucial role in shaping the universe on both small and cosmic scales. Today, we focus on one of the most extraordinary examples of these cosmic leviathans, Westerlund 1-26. Westerlund 1-26 is not just another star among billions in the Milky Way. It is a cosmic phenomenon that captures the imagination of astronomers and stargazers alike. Its immense size, extreme properties, and dramatic evolutionary stage make it an unparalleled subject of study. To understand why this star is so fascinating, we need to first appreciate what makes massive stars so significant in the grand tapestry of the universe. Stars are essentially nuclear furnaces, converting hydrogen into helium through fusion processes at their cores. This energy is what produces light, heat, and the complex interactions that sustain the star for millions to billions of years. But not all stars are created equal. Massive stars, though several times the mass of our Sun, live fast and die young, often ending their lives in spectacular supernova explosions. Their short, intense lifespans make them rare and precious laboratories for studying extreme physics and the life cycles of matter in the cosmos. Massive stars like Westerlund 1-26 are extraordinary because they push the limits of what a star can be. They are rare jewels in the cosmic landscape, often found in clusters that were born from dense molecular clouds, where conditions favored the formation of high-mass stars. Their immense gravity, combined with powerful radiation pressure, drives incredible stellar winds that shape their surroundings, blow vast cavities in interstellar space, and seed their environments with elements heavier than helium, elements that are essential for the formation of planets and, ultimately, life. In essence, these stars are not just isolated phenomena, they are active agents of cosmic evolution. Each one is a story of creation, transformation, and inevitable destruction, echoing the cycles of life on a universal scale. What makes Westerlund 1-26 particularly captivating is its scale and extremity. Among the already impressive roster of massive stars, it stands out due to its enormous radius, making it one of the largest stars ever measured in terms of sheer volume. While its mass may not be the highest among supergiants, its size stretches the imagination. If placed at the center of our solar system, it could extend beyond the orbit of Jupiter, encompassing Mercury, Venus, Earth, Mars, and the asteroid belt within its gaseous envelope. The sheer magnitude of this star challenges not only our sense of scale but also our understanding of stellar physics, as stars of this size behave differently from smaller, more familiar stars like our Sun. To truly appreciate Westerlund 1-26, we must also understand the environment it inhabits. It is not a lone wanderer. It resides in the heart of a stellar nursery, among other massive stars in the Westerlund 1 cluster, a young, dense collection of stars born from the same cosmic cloud. The cluster itself is a treasure trove for astronomers, providing a laboratory for studying how massive stars interact, evolve, and sometimes even collide or merge over time. By studying stars like Westerlund 1-26 within this cluster, scientists can piece together the complex puzzle of how the most extreme stars live, influence their surroundings, and eventually die, often in dramatic explosions that reshape their galactic neighborhoods. Another remarkable aspect of stars like Westerlund 1-26 is their role as cosmic lighthouses. Despite being thousands of light-years away, their immense luminosity allows them to shine across vast stretches of space. They are beacons that help astronomers trace the structure of the Milky Way and understand the distribution of massive stars throughout the galaxy. Yet, paradoxically, despite their brightness, they can be remarkably elusive due to intervening clouds of gas and dust that obscure their light, especially in visible wavelengths. This duality, being both incredibly luminous yet challenging to observe, adds to the mystique and allure of such stars. In popular imagination, massive stars evoke both awe and humility. They are tangible reminders of the scale of the universe, of how tiny and fleeting human existence is compared to the cosmic forces that shape galaxies. Westerlund 1-26, with its mind-boggling size, serves as a symbol of extremes, pushing the boundaries of what is possible in stellar evolution and physics. It embodies the extraordinary outcomes of nature's creativity, illustrating the delicate interplay between gravity, nuclear fusion, and cosmic time. By studying it, we gain not only scientific insights but also a profound sense of perspective, appreciating the majesty and mystery of the universe. The story of Westerlund 1-26 is more than a tale of size or brightness. It is a story of cosmic life at the edge of possibility, a star that has burned through the hydrogen in its core, swollen to an unimaginable size, and will eventually face a dramatic end that may ripple across its galactic neighborhood. In the coming segments, we will dive deeper into the specifics of this star, its location, physical characteristics, evolutionary journey, and the scientific fascination it inspires. But even at this introductory level, one thing is clear: Westerlund 1-26 is not just a star. It is a monumental cosmic phenomenon that challenges our understanding and ignites our imagination. Westerlund 1-26 is a red supergiant star of staggering proportions, a celestial titan that defies ordinary understanding of size and scale. Unlike smaller, more common stars, red supergiants are in an advanced stage of stellar evolution, having exhausted the hydrogen in their cores. This exhaustion triggers the expansion of the star's outer layers, allowing it to balloon to unimaginable dimensions. In the case of Westerlund 1-26, its radius is estimated to be more than 1,500 times that of the Sun, making it one of the largest stars ever observed in terms of sheer volume. To put this into perspective, if it were placed at the center of our solar system, its outer layers would engulf not just Mercury and Venus, but Earth, Mars, and even extend beyond Jupiter's orbit, enveloping the asteroid belt in its fiery embrace. Such a scale is difficult to grasp, yet it underscores the extremes that nature can reach in stellar evolution. Being a red supergiant also means that Westerlund 1-26 has a relatively cool surface temperature compared to smaller, hotter stars like the Sun. Its surface hovers around 3,500 Kelvin, giving it the deep, ruddy color that characterizes red supergiants. This cooler temperature, coupled with its massive size, contributes to its unique luminosity profile. It is enormously bright overall, shining hundreds of thousands of times more luminously than the Sun, yet the light is spread over a vast surface area, giving it a reddish glow rather than the intense white or blue brilliance of hotter stars. This combination of traits, immense size, cooler temperature, and intense luminosity, is what makes Westerlund 1-26 such a fascinating object for astronomers seeking to understand the limits of stellar physics. Westerlund 1-26 resides within the Westerlund 1 cluster, a remarkable assembly of young, massive stars all formed from the same giant molecular cloud. This cluster itself is a jewel of our galaxy, containing numerous supergiants, Wolf-Rayet stars, and other extreme stellar objects that are rarely seen in the Milky Way. The cluster is relatively compact, meaning that many of its most massive stars are in close proximity, interacting gravitationally and influencing each other's evolution. Westerlund 1-26 stands out even in this extraordinary environment, not because it is the most massive star in the cluster. It is not, but because its radius and evolutionary state are exceptional. Its bloated envelope, a product of its late-stage evolution, sets it apart visually and physically, marking it as a star that has pushed the boundaries of what a red supergiant can become. Astronomers study stars like Westerlund 1-26 not just for their size but for what they reveal about the life cycles of massive stars. As a red supergiant, it has already passed through several key evolutionary stages. After forming from a dense pocket of gas in its natal cloud, it spent millions of years as a hot, luminous main sequence star, fusing hydrogen into helium in its core. Once the hydrogen was depleted, the core contracted under gravity, and the outer layers expanded dramatically. This expansion leads to complex processes within the star, including convective currents that transport energy from the core outward and cause surface instabilities. These instabilities often result in variability in the star's brightness and mass loss through stellar winds, processes that are critical in shaping both the star's final fate and the surrounding environment. The classification of Westerlund 1-26 as a red supergiant is significant because it situates the star in a rare and extreme category of stellar evolution. Red supergiants are precursors to some of the most energetic events in the universe, including supernovae. While stars like the Sun will end their lives quietly as white dwarfs, massive stars like Westerlund 1-26 face violent deaths, exploding in titanic supernovae that release enormous amounts of energy and forge heavy elements in the process. This means that Westerlund 1-26 is not only an object of scale and beauty, but also a cosmic factory contributing to the chemical enrichment of the Milky Way. Its sheer existence provides astronomers with invaluable data on how stars of this magnitude evolve, lose mass, and ultimately end their lives, offering a glimpse into processes that occur on timescales far exceeding human lifespans. Understanding Westerlund 1-26 requires careful observation across multiple wavelengths. Its enormous size and red hue make it an ideal target for infrared studies, as much of its light is absorbed and re-emitted by surrounding dust and gas. Observations in visible light are challenging because interstellar dust between the star and Earth obscures much of its radiation. Using advanced telescopes and techniques, astronomers have been able to estimate its radius, luminosity, and surface properties, confirming its place among the giants of the galaxy. These studies not only reveal the physical properties of Westerlund 1-26 but also help astronomers refine models of stellar evolution, particularly in the high-mass regime where traditional theories often encounter complications. Westerlund 1-26 resides in a fascinating and somewhat hidden corner of our galaxy, the Milky Way. It is located approximately 15,000 light-years away from Earth, which is relatively close on the scale of the universe, but still far enough that it appears as a faint point of light in the night sky without the aid of powerful telescopes. To place that distance into perspective, light traveling from Westerlund 1-26 has been journeying toward us since long before humans even walked the Earth, crossing the vast expanse of space at nearly 300,000 kilometers per second. This immense separation highlights one of the intriguing aspects of astronomy. When we observe distant stars like Westerlund 1-26, we are essentially looking back in time, witnessing these colossal objects as they existed tens of thousands of years ago. Its home lies within the constellation ARA, a lesser-known constellation in the southern sky. ARA is Latin for altar, and while it may not be as famous as Orion or Ursa Major, it contains a surprising number of deep sky treasures, including massive stars, clusters, and nebulae. Westerlund 1-26 and its parent cluster, Westerlund 1, occupy a particularly rich and crowded region of the Milky Way, where star formation has been especially prolific over the last few million years. This placement deep in the galactic plane means that the cluster is heavily obscured by interstellar dust, which absorbs much of the starlight and makes visible light observations challenging. Infrared astronomy has thus been essential in penetrating this veil, revealing the incredible population of massive stars, including Westerlund 1-26, within the cluster. Visualizing its location within our galaxy helps convey just how embedded it is in the Milky Way's dense stellar disk. Imagine a flattened, spiral-shaped galaxy, with swirling arms of stars, gas, and dust. Westerlund 1-26 lies in one of these spiral arms, not in the outer reaches but closer to the galactic center, in a bustling neighborhood teeming with other massive stars. This environment is both a product of and a contributor to ongoing star formation, with Westerlund 1-26 standing as one of the most extreme examples of stellar growth in this region. Its proximity to the galactic plane also means that it is subject to strong gravitational interactions with neighboring stars and molecular clouds, shaping its evolution and that of the surrounding stellar population. Despite its distance and the obstacles posed by interstellar dust, astronomers have mapped Westerlund 1-26 with remarkable precision. Its coordinates place it firmly within the Milky Way, and by combining observations from infrared and radio wavelengths, scientists have been able to situate it relative to the spiral arms, showing its embedded position in one of the galaxy's most massive and active star-forming regions. These visualizations not only underscore the star's place in the broader galactic structure but also highlight the intricate cosmic web in which it exists, a dynamic, interactive environment where the life and death of stars like Westerlund 1-26 shape the evolution of entire regions of the galaxy. The location of Westerlund 1-26 is therefore more than just a point on a star map. It represents a stellar giant living in a dense, vibrant, and extreme neighborhood, influenced by both its cluster companions and the galaxy itself. Its distance, while immense in human terms, allows astronomers to study a microcosm of massive stellar evolution in a way that is representative of similar regions throughout the Milky Way. Through careful observation and advanced modeling, scientists can not only locate Westerlund 1-26 but also understand the role it plays in the cosmic tapestry, from enriching the surrounding medium with heavy elements to providing a laboratory for the physics of extreme stars. Westerlund 1-26 does not exist in isolation. It is part of an extraordinary stellar community known as the Westerlund 1 cluster, one of the most massive and intriguing star clusters in our galaxy. This cluster is a relatively young assembly of stars, estimated to be only about 3 to 5 million years old, which is extremely young in cosmic terms. Despite its youth, Westerlund 1 has already produced an impressive population of massive, evolved stars, including a remarkable number of red supergiants, yellow hypergiants, Wolf-Rayet stars, and other exotic stellar types. The sheer diversity and number of extreme stars make this cluster an astrophysical laboratory, allowing astronomers to study the life cycles of the most massive stars all in one place. The cluster is incredibly dense, packed with stars in a relatively small region of space. This density not only increases the likelihood of gravitational interactions among stars but also contributes to the cluster's dynamic evolution. Massive stars like Westerlund 1 to 26 exert strong gravitational forces and release prodigious amounts of energy through radiation and stellar winds, affecting the surrounding interstellar medium. Over time, these interactions can trigger further star formation or, conversely, disperse gas clouds and limit the birth of new stars. This makes Westerlund 1 not just a collection of stars, but a living, evolving system whose members influence one another in profound ways. One of the defining characteristics of the Westerlund 1 cluster is its population of supergiants. Among its members are several red supergiants similar to Westerlund 1 to 26, along with blue supergiants and other massive evolved stars. This range of stellar types provides a snapshot of the life cycle of massive stars at different stages of evolution. In a sense, Westerlund 1 is a stellar timeline. By studying its various members, astronomers can trace the transformations that stars undergo as they burn through their nuclear fuel, expand, shed mass, and eventually explode as supernovae. It's rare to find such a concentrated assembly of extreme stars, which makes Westerlund 1 a critical reference point for understanding how massive stars evolve under similar initial conditions. The cluster's mass and composition are also extraordinary. Estimates suggest that Westerlund 1 contains tens of thousands of solar masses worth of stars, making it one of the most massive young clusters in the Milky Way. Its richness in heavy stars ensures that the environment is intensely energetic. The combined radiation, stellar winds, and eventual supernovae of these stars inject enormous amounts of energy and material into the surrounding galactic space. This not only influences the immediate neighborhood but also contributes to the chemical evolution of the Milky Way, seeding the interstellar medium with elements essential for future generations of stars and planets. Westerlund 1 has also captured the attention of astronomers because of its obscured nature. Located deep within the Milky Way's disk, the cluster is heavily shrouded by interstellar dust, which blocks much of its light in visible wavelengths. Infrared and radio observations have been crucial for studying its members, including Westerlund 1 to 26. These observations reveal not only the population of massive stars but also complex interactions within the cluster, such as colliding winds from binary systems and the formation of nebulae from mass ejected by supergiants. Such studies help refine models of stellar evolution, particularly for massive stars, which are notoriously difficult to predict in terms of lifespan, size, and final fate. Being part of this cluster amplifies the significance of Westerlund 1 to 26. Its interactions with neighboring stars, the cluster's gravitational dynamics, and the shared history of formation provide context for understanding the star's evolution. Unlike isolated stars, which may have formed in relative solitude, stars in clusters like Westerlund 1 are subject to environmental effects that can accelerate or alter their evolution. This makes Westerlund 1 to 26 not only a record of its own life but also a piece of a larger cosmic narrative that includes dozens of other extreme stars, each contributing to a complex, interwoven story of stellar birth, life, and death. Studying Westerlund 1 thus allows astronomers to investigate extreme astrophysical phenomena in a controlled, natural laboratory. From the rare red supergiants to the energetic Wolf-Rayet stars and the cluster's potential for future supernovae, Westerlund 1 presents a microcosm of high-mass stellar evolution. Westerlund 1 to 26, as one of the most extreme members, acts as a focal point within this cosmic ecosystem, demonstrating what is possible when nature pushes the boundaries of size, energy, and luminosity. Westerlund 1 to 26 is so vast that conventional comparisons almost fail to convey its enormity, yet visualizing it in terms of our Sun helps put its scale into perspective. The Sun, a fairly typical G-type main sequence star, has a radius of about 696,000 kilometers. In contrast, Westerlund 1-26 is estimated to have a radius of roughly 2,000 times that of the Sun, although estimates vary depending on observational methods. To understand what this means, imagine placing the Sun at the center of Westerlund 1-26. The Sun would appear as a tiny, almost imperceptible speck within the immense, bloated envelope of the supergiant. Every planet in our solar system up to Jupiter would be engulfed inside the star, orbiting within layers of hydrogen and helium gas that extend hundreds of millions of kilometers from its core. Mercury, Venus, Earth, Mars, the asteroid belt, and even Jupiter would all fit comfortably inside Westerlund 1-26, illustrating its truly astronomical proportions. If one were to attempt a visual representation, the Sun would be as small at the center, while the outer layers of Westerlund 1-26 would form a gigantic, diffuse sphere encompassing vast distances that dwarf the familiar scale of our solar system. This kind of graphic is particularly effective for conveying just how extreme red supergiants can become compared to smaller, more familiar stars. While our Sun radiates energy steadily and occupies a relatively modest volume, Westerlund 1-26 has swelled to a size that is nearly unimaginable, demonstrating how stars evolve dramatically in the later stages of their life cycles. The size comparison also emphasizes the difference between mass and volume in stars. While Westerlund 1-26 is enormous in terms of radius, its mass is only about 30 to 40 times that of the Sun, which highlights an important aspect of stellar physics. A star can be massive in volume without being proportionally massive in terms of material. Its extreme radius is largely due to the expansion of its outer layers after exhausting hydrogen in the core, not because it has accumulated an extraordinary amount of matter. This inflated envelope makes it highly luminous but also unstable, subject to pulsations, convection currents, and powerful stellar winds that gradually peel away layers of its outer material. Comparing Westerlund 1-26 to the Sun also underscores the dramatic changes a massive star undergoes over its life. While the Sun will eventually expand into a red giant billions of years from now, it will never reach the scale of Westerlund 1-26. The sheer size of this star exemplifies the extremes of stellar evolution, particularly for stars born with large initial masses. Its volume and surface area are so immense that its total output of energy dwarfs anything produced by the Sun, even though the surface temperature is lower. This results in a star that is enormously radiant yet cooler in color, giving it the deep red appearance characteristic of red supergiants. Visualizing the Sun inside Westerlund 1-26 also provides an intuitive understanding of the physical scale at play. It's one thing to discuss numbers in kilometers or solar radii, but placing a familiar object like the Sun inside the star makes the enormity tangible. It highlights how small our solar system is on a cosmic scale and how extreme conditions become in the universe's most massive stars. Such comparisons are crucial not just for public understanding but also for astrophysicists, as they illustrate the relationship between a star's size, luminosity, and evolutionary stage in a way that is both dramatic and scientifically meaningful. One of the most fascinating aspects of stars like Westerlund 1-26 is the complex relationship between mass and radius. At first glance, it might seem intuitive to assume that the largest stars must also be the most massive. After all, if a star is physically enormous, it should contain more matter, right? But in reality, a star's radius and mass are not directly proportional. Westerlund 1-26 beautifully illustrates this principle. While it is one of the largest stars ever observed in terms of volume, its mass is only about 30 to 40 times that of the Sun. That's extraordinarily massive compared to the Sun, yet it is far from being the heaviest star known. There are stars, particularly some Wolf-Rayet stars and luminous blue variables, that pack in over 100 solar masses, yet have much smaller radii. The reason for this discrepancy lies in stellar evolution and structure. A star's radius is determined not only by its total mass but also by the internal processes occurring in its core and envelope. In the case of red supergiants like Westerlund 1-26, the star has exhausted hydrogen in its core, leading to core contraction and the expansion of the outer layers. This creates an enormous, tenuous envelope that drastically increases the star's volume without a corresponding increase in mass. Essentially, the outer layers are puffed up and spread across an immense radius, making the star look colossal while the bulk of its mass remains concentrated in the denser core. This effect is particularly pronounced in evolved stars because the envelope is supported largely by radiation pressure and thermal expansion rather than gravitational compression. In simpler terms, The star's outer layers are incredibly spread out, making them lightweight relative to their volume. Imagine a balloon filled mostly with hot gas. It can be huge, but the material itself doesn't weigh very much. That is analogous to what is happening with Westerlund 1-26. Its sheer size is impressive, but in terms of raw mass, it is modest compared to some smaller but denser massive stars. This distinction between mass and radius also has significant consequences for the star's future evolution and stability. Large, diffuse stars like Westerlund 1-26 are prone to strong stellar winds and episodic mass loss. The tenuous outer layers are easily blown away into space, forming nebulae and enriching the surrounding interstellar medium with heavy elements. This mass loss gradually reduces the star's total mass, even as it maintains an enormous radius until it reaches the final stages of its life. In contrast, more compact massive stars can retain their mass longer, evolving differently and producing different types of supernovae or black holes. The contrast between mass and radius also challenges simple assumptions in astronomy. Many people intuitively equate biggest star with most massive star, but stars like Westerlund 1-26 highlight the complexity of stellar physics. The enormous radius can give the impression of unmatched power or mass, but in reality, the star's energy output, gravity, and evolutionary trajectory depend on both mass and internal structure. Studying this relationship helps astronomers refine models of stellar evolution, particularly for high-mass stars nearing the end of their lives. It shows that volume alone does not determine the fate or physical behavior of a star. Its mass, composition, and core processes are equally, if not more, critical. In summary, Westerlund 1-26's extraordinary size makes it an awe-inspiring object, but its moderate mass relative to other massive stars emphasizes an important lesson. Enormous radius does not equal enormous mass. Understanding this distinction is key to appreciating the diversity of massive stars, the physics of their expansion, and the intricate ways in which they interact with their environments. It's a humbling reminder that appearances can be deceiving in the cosmos. What looks colossal on the outside may contain hidden subtleties at the core. Westerlund 1-26 is not just remarkable for its size, it is also a cosmic powerhouse of light and energy. Its luminosity is staggering, estimated to be hundreds of thousands of times brighter than the Sun. To put that into perspective, if you were to replace the Sun with Westerlund 1-26 at the center of our solar system, the energy output would be so immense that the Earth, and all the planets within its radius, would be instantly incinerated. Even though the star's surface temperature is relatively cool for a massive star, around 3,500 Kelvin, its sheer enormous surface area allows it to radiate incredible amounts of energy across the electromagnetic spectrum. Luminosity in stars is a function of both temperature and surface area, as described by the Stefan Boltzmann law. While Westerlund 1-26's temperature is much lower than that of hotter, blue supergiants or main sequence O-type stars, its gigantic radius more than compensates, allowing it to shine with unparalleled brilliance. The combination of large size and high energy output creates a star that dominates its local environment, illuminating nearby dust and gas clouds, and influencing the formation and evolution of neighboring stars in the Westerlund 1 cluster. This incredible luminosity is also a key indicator of the star's evolutionary stage. As a red supergiant, Westerlund 1-26 has expanded enormously, causing a drop in surface temperature but maintaining a massive energy output due to the enormous radiating surface. The light it emits is mostly in the red and infrared wavelengths, which is why observations of red supergiants often rely on infrared telescopes to penetrate the surrounding dust and capture their full brightness. This energy output is so intense that it drives strong stellar winds, ejecting material into space at high velocities and contributing to the enrichment of the surrounding interstellar medium. Westerlund 1-26's luminosity also highlights the dramatic contrast between stars of similar mass. For example, while stars of 30 to 40 solar masses can remain relatively compact and hot, radiating mostly in ultraviolet light, the red supergiant phase amplifies the star's total radiative output by leveraging its immense surface area. In this way, a red supergiant like Westerlund 1-26 demonstrates that size can enhance luminosity, even when temperature decreases, creating some of the most radiant stars in the universe. From an observational perspective, the star's luminosity is both a blessing and a challenge. Its brightness makes it detectable over vast distances, even 15,000 light-years away, but interstellar dust obscures much of its light in visible wavelengths, necessitating infrared imaging to fully appreciate its true radiance. Advanced instruments allow astronomers to quantify this luminosity accurately, revealing that despite its cool surface temperature, Westerlund 1-26 outshines many smaller, hotter stars by enormous factors. The luminosity of Westerlund 1-26 is also a precursor to its eventual fate. Massive stars emit incredible amounts of energy throughout their lives, and this energy output contributes to internal instability, mass loss, and ultimately the conditions that will lead to their supernova explosion. In the case of Westerlund 1-26, its radiative power is a tangible reminder of the tremendous forces at work within these giant stars. It illuminates the cosmos while also sculpting it, pushing material into space, influencing star formation, and leaving an indelible mark on its galactic neighborhood. In essence, Westerlund 1-26's luminosity is a perfect example of cosmic extremes. A relatively cool star, immense in size, producing energy output that dwarfs most other stars in the galaxy. It exemplifies how massive, evolved stars combine volume, temperature, and nuclear fusion to create radiant beacons that both awe and inform astronomers studying the life cycles of the universe's giants. Westerlund 1-26 is classified as a red supergiant, a designation that is closely tied to its surface temperature. Unlike hotter stars, which can reach tens of thousands of Kelvin and shine blue or white, Westerlund 1-26 has a relatively cool surface temperature of about 3,500 Kelvin. While this may seem extraordinarily hot from a human perspective, in the world of stars, it is considered cool. This lower temperature is what gives the star its characteristic deep red hue, a hallmark of red supergiants. The color is not just an aesthetic trait, it's a physical indicator of the star's evolutionary stage, composition, and surface conditions. The relatively cool temperature of Westerlund 1-26 is a direct consequence of its enormous expansion. After the star exhausted the hydrogen in its core, nuclear fusion shifted to shell burning around the core. This change caused the star's outer layers to expand dramatically, increasing its radius to over 1,000 times that of the Sun. As the surface area grows, the energy from the core is spread over much larger volume, which leads to a decrease in surface temperature. Essentially, the star becomes cooler at its outer layers even while the core remains intensely hot and active, fusing heavier elements. This cooler temperature also affects the star's spectral characteristics. The star emits more strongly in the red and infrared part of the electromagnetic spectrum, which is why astronomers studying Westerlund 1-26 rely on infrared telescopes to capture its full luminosity. Its spectral type, often classified as M-type supergiant, corresponds to stars that are both massive and evolved, with atmospheres dominated by molecules that would not survive in hotter stars. The presence of these molecules, like titanium oxide, further enhances the reddish appearance, giving astronomers an additional tool for understanding its composition and physical properties. The surface temperature is also closely linked to stellar instability. Red supergiants like Westerlund 1-26 are prone to pulsations, convection currents, and massive stellar winds because the cooler, extended outer layers are not as tightly bound by gravity as in smaller or hotter stars. These processes lead to the ejection of material into space, forming circumstellar shells and contributing to the enrichment of the surrounding interstellar medium. The combination of low temperature, immense size, and strong stellar winds is what makes red supergiants such dynamic and influential members of the galaxy. In comparison to other stars, Westerlund 1-26's surface temperature highlights the diversity of stellar characteristics. Hotter stars, such as blue supergiants or O-type stars, are compact, intensely luminous in ultraviolet light, and short-lived due to rapid fuel consumption. Cooler red supergiants, on the other hand, expand to immense sizes, radiate primarily in the red and infrared, and serve as the penultimate stage before a star's dramatic death as a supernova. Westerlund 1-26, with its relatively cool surface temperature, exemplifies this stage vividly, making it a textbook example of the extreme physics that govern massive stellar evolution. Understanding the surface temperature of Westerlund 1-26 also helps explain why it is so visually striking despite its distance of 15,000 light-years. The deep red color, combined with its enormous size, makes it one of the most luminous red supergiants known, and allows astronomers to study its structure and evolution even through layers of interstellar dust. Its temperature is a reminder that brightness alone does not equate to heat, and that the appearance of a star is intimately connected to both its size and evolutionary state. Westerlund 1-26 is a stellar elder in the cosmic sense, firmly positioned in the late stages of its life cycle. Like all stars, it began its life as a dense pocket of gas and dust within a molecular cloud. Over millions of years, gravitational forces caused the material to collapse, igniting nuclear fusion in its core. Initially, it spent the majority of its life on the main sequence, fusing hydrogen into helium in a stable equilibrium. For massive stars, however, this phase is relatively short-lived. Whereas our Sun will remain on the main sequence for about 10 billion years, stars like Westerlund 1-26 burn through their hydrogen in just a few million years due to their enormous mass and energy output. Once the hydrogen fuel in its core was exhausted, Westerlund 1-26 underwent dramatic structural changes. The core contracted under gravity, increasing in temperature and pressure, while the outer layers expanded enormously. This expansion is a defining characteristic of red supergiants, transforming the star from a relatively compact blue or yellow supergiant into an enormous, cool, and luminous red giant. Its radius ballooned to over 1,000 times that of the Sun, making it one of the largest known stars in the universe. This stage represents the star's attempt to balance the intense energy produced by fusion in its core against the pull of gravity. During this phase, the star begins to fuse heavier elements in shells surrounding its core. After hydrogen fusion, it progresses to helium fusion, producing carbon and oxygen. Eventually, for the most massive stars, this process continues through successive shells, generating increasingly heavier elements such as neon, magnesium, silicon, and finally iron. Each stage occurs more rapidly than the last, with the outer layers becoming increasingly unstable as energy from the core pushes outward. Westerlund 1-26's enormous luminosity and stellar winds are a direct result of this late-stage fusion, as energy struggles to escape from the dense core to the bloated outer envelope. The late stages of stellar evolution for red supergiants are also marked by significant mass loss. Convection and pulsations in the extended outer layers cause material to be ejected into space at high velocities. This process not only reduces the star's mass over time, but also contributes to the formation of nebulae and enriches the surrounding interstellar medium with heavy elements that will eventually be recycled into new stars and planets. Observations of Westerlund 1-26 show that it is shedding material at a prodigious rate, creating complex structures around the star that are visible in infrared and radio wavelengths. Westerlund 1-26's evolutionary stage also makes it an important object for understanding the fate of massive stars. Unlike smaller stars, which quietly transition into white dwarfs, red supergiants of this mass are destined for explosive deaths as supernovae. The core, after successive fusion stages, eventually becomes dominated by iron, which cannot produce energy through fusion. Once the core collapses under its own gravity, a catastrophic explosion occurs, releasing enormous amounts of energy and dispersing the star's outer layers into space. For Westerlund 1-26, this future event is inevitable, although the exact timing, whether in thousands or tens of thousands of years, is uncertain. Studying stars like Westerlund 1-26 in their late evolutionary stages gives astronomers critical insights into stellar life cycles, nucleosynthesis, and the mechanisms behind supernovae. By observing its luminosity, mass loss rates, pulsations, and spectral characteristics, scientists can refine theoretical models of high-mass stellar evolution. Westerlund 1-26 thus serves as both a cosmic laboratory and a living illustration of the life cycle of the universe's most massive stars, burning brightly, expanding dramatically, and ultimately approaching the spectacular final act of stellar death. Massive stars like Westerlund 1-26 live life in the fast lane, burning through their fuel at an astonishing rate compared to smaller stars like our Sun. While the Sun's stable main sequence lifetime stretches nearly 10 billion years, a star of Westerlund 1-26's mass may exhaust its nuclear fuel in only a few million years. This accelerated life cycle is a direct consequence of its extreme mass. The more massive a star, the higher the core pressure and temperature, which in turn drives fusion reactions at a far faster pace. In effect, the star is burning through its energy reserves at a furious pace, living brilliantly but briefly on the cosmic timescale. The concept of short life in this context is relative, because even a few million years might seem immense from a human perspective. However, in the lifetime of the universe, which spans over 13 billion years, Westerlund 1-26's existence is fleeting. Its intense luminosity and rapid fuel consumption mean that every phase of its life proceeds quickly, From its initial formation within a molecular cloud, through the main sequence stage, and now into its red supergiant phase, each stage occupies only a small fraction of cosmic time. The star's life, though short, is extraordinarily eventful, marked by intense energy output, dramatic expansion, and powerful interactions with its environment. The brevity of Westerlund 1-26's life also emphasizes why such stars are relatively rare in the galaxy. At any given moment, only a few dozen of these extreme red supergiants exist within the Milky Way. The combination of high mass, rapid evolution, and eventual violent death ensures that massive stars spend only a short time in observable stages like the red supergiant phase. This rarity makes Westerlund 1-26 an invaluable target for astronomers, offering a glimpse into phenomena that occur in fleeting windows of cosmic history. This short life expectancy also has profound implications for the star's future evolution. The faster a star consumes its fuel, the sooner it will reach the end of its life, collapsing under its own gravity to trigger a supernova explosion. In the case of Westerlund 1-26, the remaining lifetime is likely on the order of hundreds of thousands to a few million years, a mere heartbeat in the scale of galactic evolution. When it does explode, the event will release enormous amounts of energy, forge heavy elements, and potentially leave behind a neutron star or black hole. In this way, even though its existence is brief, its impact on the galaxy is profound, seeding the surrounding space with material that will contribute to the next generation of stars and planets. Massive stars like Westerlund 1-26 demonstrate a fundamental principle of astrophysics. The more massive the star, the shorter its lifespan. This inverse relationship is a key factor in understanding stellar populations, galaxy evolution, and the chemical enrichment of the cosmos. By studying stars in these fleeting late life stages, astronomers can better predict supernova rates, the distribution of heavy elements, and the dynamics of star clusters. In essence, Westerlund 1-26's short life is not a limitation. It is a window into the extraordinary processes that shape our galaxy on both small and grand scales. When comparing Westerlund 1-26 to other well-known red supergiants, Betelgeuse often comes to mind. Betelgeuse, the bright reddish star marking the shoulder of Orion, is one of the most famous and observable red supergiants in the night sky. It has captured public imagination due to its brightness, distinctive color, and proximity, just about 700 light-years away, making it far closer than Westerlund 1-26. While Betelgeuse is enormous by human standards, with a radius roughly 1,000 times that of the Sun, Westerlund 1-26 dwarfs it in terms of sheer size, with a radius exceeding 1,500 to 2,000 solar radii. Visual comparisons between the two stars are striking. If Betelgeuse were placed at the center of our solar system, it would engulf Mercury, Venus, Earth, and possibly reach Mars. Westerlund 1-26, by contrast, would extend beyond Jupiter's orbit, swallowing the inner planets and the asteroid belt in its expansive envelope. While both stars are red supergiants, their luminosity and energy output differ dramatically. Betelgeuse shines roughly 100,000 times brighter than the Sun, impressive by any standard but still significantly less than Westerlund 1-26's output, which exceeds hundreds of thousands of solar luminosities. This difference stems not only from Westerlund 1-26's larger radius but also from subtle differences in mass, age, and evolutionary stage. Betelgeuse, while nearing the end of its life, is slightly less massive and closer to its supernova phase in human observational terms, making it a fascinating but distinct point of comparison for astronomers studying massive stars. Another point of distinction lies in distance and observational accessibility. Betelgeuse, being relatively close to Earth, allows astronomers to study surface features, pulsations, and even irregular brightness changes in detail. Westerlund 1-26, on the other hand, is about 15,000 light-years away, deeply embedded in the Westerlund 1 cluster and obscured by interstellar dust. Observations require infrared or radio wavelengths, making it harder to visualize directly, but still enabling astronomers to measure its luminosity, radius, and mass loss behavior. This contrast illustrates how distance and environmental factors can shape our understanding of even similar types of stars. Comparing the two also provides insights into stellar evolution. Both stars have exhausted core hydrogen and expanded into red supergiants, but Westerlund 1-26, due to its slightly higher mass and cluster environment, may exhibit stronger mass loss, larger radius, and different pulsation patterns. These differences help scientists understand the diversity within the red supergiant category and highlight how even stars with similar compositions can evolve in distinct ways based on mass, age, and surrounding environment. Visualizations that place both stars side by side are particularly effective at conveying the scale. Imagine the Sun as a tiny Betelgeuse surrounding it and reaching roughly to Mars' orbit, and then Westerlund 1-26 extending well past Jupiter. This scaling not only emphasizes the extraordinary size of Westerlund 1-26 but also helps the human mind grasp the extreme diversity of stellar giants in the universe. Such comparisons also spark imagination. If these stars were placed at the center of our solar system, the inner planets would be swallowed by their fiery envelopes, providing a tangible sense of the scale and energy of red supergiants. In essence, Westerlund 1-26 and Betelgeuse share the same classification but occupy very different positions on the spectrum of red supergiants. Betelgeuse serves as a nearby, observable prototype, while Westerlund 1-26 represents the extreme end of the size and luminosity scale. Together, they illustrate the variety and scale of massive stars in the universe, and how factors like mass, environment, and age shape the final stages of stellar evolution. Studying Westerlund 1-26 presents a unique set of observational challenges that make it far more difficult to analyze than nearby stars like Betelgeuse. First and foremost, its sheer distance of approximately 15,000 light-years means that its light has to travel across an immense stretch of space before reaching Earth. Over such distances, starlight is attenuated and scattered by the interstellar medium, a mixture of gas, dust, and cosmic particles that pervades the Milky Way. This obscuration is particularly severe for stars like Westerlund 1-26, which reside deep within the galactic plane, a dense region filled with dust clouds that absorb visible light and hide many stars from optical telescopes. As a result, traditional observations in the visible spectrum often fail to capture the full structure, luminosity, or features of the star. To circumvent this problem, astronomers rely heavily on infrared and radio observations. Infrared light can penetrate dust clouds that block visible wavelengths, allowing researchers to study the star's size, luminosity, and surrounding environment with much greater clarity. Space-based infrared telescopes, such as the Spitzer Space Telescope, and ground-based observatories equipped with adaptive optics have been instrumental in revealing Westerlund 1-26's characteristics. These instruments can detect the heat radiated by the star and its circumstellar material, providing a window into processes like mass loss, pulsations, and the structure of its massive envelope. Without such specialized technology, much of what we know about this red supergiant would remain hidden. The star's location within a dense cluster also complicates observations. Westerlund 1 contains dozens of other massive stars in close proximity, many of which are also luminous red and blue supergiants. Separating the light and signals from Westerlund 1-26 from those of its neighbors requires sophisticated data analysis and high-resolution imaging. Otherwise, the dense stellar environment can make it difficult to determine individual properties, such as radius, luminosity, or variability. Observers must carefully model the contributions of surrounding stars, interstellar dust, and potential nebular material to accurately characterize Westerlund 1-26. Moreover, the star's variable nature adds another layer of complexity. Red supergiants often experience pulsations and surface instabilities that cause fluctuations in brightness, sometimes over weeks or months. These variations can be subtle or pronounced, and measuring them requires consistent, long-term monitoring. Combined with the star's obscured location and extreme distance, capturing these variations is a challenge that demands patience, precision, and sophisticated instrumentation. Finally, the extreme size and low surface temperature of Westerlund 1-26 mean that much of its radiation is emitted in the infrared, rather than the optical range where traditional telescopes are most sensitive. Detecting and quantifying the light from such a star therefore requires careful calibration of instruments, corrections for interstellar absorption, and sometimes indirect methods, such as modeling the surrounding nebulae produced by mass loss. Every observation requires consideration of multiple layers of interference, from the Earth's atmosphere to galactic dust, making research on Westerlund 1-26 a demanding but rewarding endeavor. Despite these challenges, astronomers have successfully measured its radius, luminosity, and mass loss rates, largely thanks to infrared imaging, spectroscopy, and high-resolution adaptive optics. These observations have allowed scientists to uncover the extraordinary properties of Westerlund 1-26 and place it in context with other red supergiants. In essence, the difficulty of studying this star highlights the interplay between cosmic scale, stellar environment, and technological innovation. It is a reminder that the universe does not always reveal its extremes easily, and understanding giants like Westerlund 1-26 requires pushing the limits of observational astronomy. Westerlund 1-26's story in modern astronomy begins with the discovery of its parent cluster, Westerlund 1, by the Swedish astronomer Bengt Westerlund in 1961. Using the telescopes available at the time, Westerlund identified a dense, compact cluster of stars in the southern constellation of Ara, noting its unusual population of massive stars. However, the cluster was heavily obscured by interstellar dust, which made detailed study difficult with the optical telescopes of that era. It wasn't until decades later, with the advent of infrared astronomy and advanced imaging techniques, that the full richness of the cluster, including Westerlund 1-26, was revealed. Westerlund 1-26 emerged as a particularly intriguing object because of its extraordinary size and luminosity. Early observations in the optical spectrum were limited by dust obscuration, but infrared observations allowed astronomers to peer through the intervening material. Using instruments sensitive to infrared light, such as the ESO Very Large Telescope, VLT, in Chilean space-based observatories, astronomers were able to measure the star's brightness, spectral characteristics, and variability. Spectroscopy, in particular, enabled researchers to determine the star's surface temperature, chemical composition, and radial velocity, providing essential clues to its evolutionary stage. Determining the size of Westerlund 1-26 required careful analysis. Because the star is so distant and its outer layers are diffuse, direct imaging of its disk is nearly impossible. Instead, astronomers relied on indirect methods, including measuring its luminosity and effective temperature, and applying the Stefan-Boltzmann law to estimate its radius. By combining these calculations with models of stellar atmospheres for red supergiants, they could derive an approximate radius exceeding 1,500 solar radii, placing it among the largest stars known. Over time, more refined measurements, including adaptive optics and interferometry, have allowed astronomers to improve estimates of both its size and mass loss rates. The star's discovery and subsequent study also relied heavily on the context provided by the cluster environment. Westerlund 1 contains dozens of massive, evolved stars whose properties can be compared against each other. By observing the relative luminosities, spectral types, and evolutionary stages of these stars, astronomers were able to confirm Westerlund 1-26's status as a red supergiant and estimate its age and mass. Its identification as one of the cluster's largest and most luminous members emerged gradually, as improved instrumentation revealed the extraordinary scale of its radius and envelope. In addition, long-term monitoring of the star has provided insights into its variability and mass loss behavior. Red supergiants often experience pulsations and episodic ejections of material, and tracking these changes over time has allowed astronomers to refine models of the star's outer envelope and its interaction with the surrounding environment. The combination of infrared imaging, spectroscopy, and theoretical modeling has transformed Westerlund 1-26 from a distant, obscured point of light into one of the most studied extreme stars in the Milky Way. The discovery history of Westerlund 1-26 illustrates a broader narrative in astronomy, that of technological progress revealing the hidden extremes of the universe. From its initial detection within the Westerlund 1 cluster to the detailed characterization of its size, luminosity, and evolutionary state, the star's story is one of persistence, innovation, and the gradual peeling away of cosmic obscuration to uncover nature's most extraordinary giants. Massive stars like Westerlund 1-26 are far from static. They are dynamic engines of matter and energy, constantly reshaping their surroundings through stellar winds and mass loss. Unlike smaller stars such as the Sun, which lose only minuscule fractions of their mass over billions of years, red supergiants shed significant amounts of material over comparatively short timescales. For Westerlund 1-26, this mass loss occurs as the outer layers of the star are ejected into space, driven by a combination of radiation pressure, convection currents, pulsations, and instabilities in its enormous envelope. Estimates suggest that red supergiants of this type can lose the equivalent of thousands of Earth masses per year, a staggering rate that profoundly affects both the star itself and its surrounding environment. The process of mass loss in Westerlund 1-26 begins in its extended, tenuous outer layers, which are loosely bound by gravity due to the star's enormous size. Convection within these layers creates giant bubbles of hot gas that rise and expand, pushing material outward. Simultaneously, the star's intense radiation exerts pressure on its outer atmosphere, accelerating particles and gas into space. These combined forces produce stellar winds, streams of charged particles and gas that flow away from the star at speeds often exceeding tens of kilometers per second. Over time, these winds remove significant portions of the star's outer mass, shaping its evolution and altering its luminosity and surface characteristics. One of the most visually striking consequences of this mass loss is the formation of circumstellar nebulae, clouds of gas and dust surrounding the star. As material is ejected, it interacts with the surrounding interstellar medium, sometimes forming arcs, shells, or filamentary structures. In the case of Westerlund 1-26, infrared and radio observations have revealed evidence of such nebulae, providing a glimpse into the star's past activity and ongoing mass ejection. These nebulae not only showcase the star's immense power but also enrich the local environment with heavy elements such as carbon, oxygen, and silicon, which are later incorporated into new stars and planets. Mass loss also has significant implications for the future evolution of Westerlund 1-26. By shedding mass, the star gradually reduces the gravitational binding of its envelope, which can lead to further expansion and increased instability. Over time, these processes can influence the timing and nature of the star's eventual supernova explosion, as well as the type of remnant it leaves behind, whether a neutron star or a black hole. The interplay between mass loss, stellar winds, and evolutionary stage makes red supergiants like Westerlund 1-26 both complex and fascinating subjects for astrophysical study. In addition, observing these winds and nebulae allows astronomers to estimate mass loss rates, surface compositions, and the chemical enrichment of the surrounding interstellar medium. By tracking the ejected material, scientists can model the star's past evolution, current state, and likely future, providing a comprehensive picture of how massive stars live, interact with their environment, and ultimately die. In this sense, Westerlund 1-26 is not just a solitary star but a cosmic sculptor, shaping its neighborhood, feeding the galaxy with heavy elements, and leaving behind visible traces of its dramatic life. In summary, mass loss and stellar winds are defining characteristics of massive red supergiants like Westerlund 1-26. Through continuous ejection of material, the star influences its cluster, forms intricate nebulae, and drives the chemical evolution of the Milky Way. These processes are essential for understanding both the star itself and the broader life cycle of matter in the galaxy, highlighting the profound interconnectedness of stars, clusters, and cosmic evolution. The life of Westerlund 1-26, magnificent as it is now, is ultimately fated for a dramatic and violent end, a supernova explosion. Like all massive stars that have exhausted the fuel in their cores, it cannot maintain equilibrium indefinitely. After millions of years of fusing hydrogen and helium, and progressing through heavier elements in successive shells, the core will eventually accumulate iron, an element that cannot release energy through fusion. Once the iron core reaches a critical mass, it can no longer support itself against the relentless pull of gravity, triggering a catastrophic core collapse that initiates the supernova. This event will release energy equivalent to billions of suns, briefly outshining the entire host galaxy and dispersing vast amounts of stellar material into the surrounding space. The precise timing of Westerlund 1-26's supernova is uncertain. While massive stars live fast and die young in cosmic terms, this young age can still span hundreds of thousands to a few million years. When the supernova occurs, it will likely be a Type II supernova, characterized by the presence of hydrogen in the ejected material, typical for red supergiants with massive hydrogen envelopes. The explosion itself will be immensely energetic, driving powerful shock waves into the surrounding interstellar medium, compressing gas, and potentially triggering new rounds of star formation in the cluster and its galactic neighborhood. The aftermath of this supernova depends largely on the mass of the remaining core. If the core is below a critical limit, roughly 2 to 3 solar masses, it will stabilize as a neutron star, an incredibly dense remnant composed almost entirely of neutrons. Neutron stars are among the most extreme objects in the universe, with masses comparable to the Sun compressed into a sphere only about 20 kilometers in diameter. If, however, the core exceeds this limit, gravity will overwhelm all opposing forces, collapsing the core into a black hole, an object with gravity so intense that not even light can escape. Either outcome would leave a permanent, extraordinary imprint on the Milky Way, marking the final transformation of this colossal star into one of the universe's most extreme remnants. The supernova explosion will also dramatically enrich the galaxy with heavy elements. During its lifetime, Westerlund 1-26 has already shed substantial mass through stellar winds, but the supernova will release newly formed elements such as oxygen, silicon, and iron into space. These elements are crucial for the formation of planets, life, and subsequent generations of stars. In this way, even after its violent death, Westerlund 1-26 will continue to shape the cosmos, seeding the Milky Way with the materials necessary for future cosmic structures. Observing and modeling stars like Westerlund 1-26 provides astronomers with valuable insights into supernova mechanisms, nucleosynthesis, and the formation of neutron stars and black holes. By understanding the mass, radius, composition, and mass loss rates of these stars before they explode, scientists can better predict the nature of the supernova and the type of remnant it will produce. Westerlund 1-26, therefore, serves as a critical laboratory for studying the end stages of massive stellar evolution, helping refine models that can be applied to countless other massive stars across the universe. In essence, Westerlund 1-26 is a star on the edge of cosmic drama. Its current state as a colossal red supergiant is a prelude to one of the universe's most spectacular events, a supernova that will transform its environment, leave behind a dense remnant, and disperse the elements forged in its core throughout the galaxy. This ultimate fate underscores both the power and impermanence of massive stars, offering a glimpse into the life cycles that shape galaxies and, ultimately, the cosmos itself. Massive stars like Westerlund 1-26 play a crucial role in shaping the galaxy and driving its chemical evolution. Throughout their lives, these stars act as cosmic furnaces, fusing lighter elements like hydrogen and helium into progressively heavier elements in their cores. When they die in supernova explosions, these newly formed heavy elements, such as carbon, oxygen, silicon, and iron, are ejected into the interstellar medium, seeding the galaxy with the building blocks for future generations of stars, planets, and even life. Without stars like Westerlund 1-26, the Milky Way would remain dominated by lighter elements, and the complex chemistry necessary for planets and organic molecules would be far less abundant. The enrichment process begins gradually during the star's lifetime. As a red supergiant, Westerlund 1-26 sheds material through stellar winds, releasing hydrogen, helium, and some heavier elements into its immediate surroundings. This mass loss forms circumstellar nebulae, which mix with the interstellar medium over time. When the star eventually ends its life in a supernova, the ejected material carries the heavier elements created during core fusion outward at tremendous speeds, dispersing them across light-years of space. These enriched regions then become fertile ground for new star formation, as the gas and dust collapse under gravity to form new stellar systems. In this way, each massive star acts as both a destroyer and creator. It dies in a violent explosion but leaves behind the raw materials for future cosmic generations. Westerlund 1-26's impact is amplified by its location within the Westerlund 1 cluster, a dense collection of massive stars. The combined winds, radiation, and eventual supernovae of the cluster's members create a highly energetic environment that can compress nearby gas clouds, triggering star formation in regions that might otherwise remain dormant. This feedback loop, where massive stars both enrich and stimulate the birth of new stars, is a central mechanism in galactic evolution. Over millions of years, these processes help shape the structure of the Milky Way, influence the distribution of chemical elements, and determine the characteristics of stellar populations in different regions of the galaxy. The heavy elements dispersed by stars like Westerlund 1-26 are also critical for planet formation. Elements such as carbon, oxygen, magnesium, and iron form the basis of terrestrial planets, asteroid belts, and the cores of gas giants. Without the enrichment from massive stars over billions of years, solar systems like our own, complete with rocky planets and the potential for life, would not exist. In essence, these stars act as cosmic alchemists, transforming the simple hydrogen and helium left over from the Big Bang into the diverse chemical palette that enables planetary systems and the chemistry of life. Moreover, the energy output of massive stars influences the dynamics of the interstellar medium. Their radiation and winds can clear away gas from star-forming regions, sculpting nebulae and creating cavities and bubbles within molecular clouds. This shaping process regulates the rate of star formation, preventing runaway collapse in some areas while compressing gas to stimulate new star birth in others. Westerlund 1-26, as one of the largest and most luminous stars in its cluster, contributes significantly to these galactic scale effects, illustrating how individual massive stars can influence their surroundings far beyond their immediate neighborhoods. In summary, Westerlund 1-26 and its fellow massive stars serve as engines of galactic evolution. Through mass loss, supernova explosions, and energetic feedback, they enrich the Milky Way with heavy elements, regulate star formation, and lay the foundation for future planetary systems. Their lives, though brief in cosmic terms, have lasting effects, demonstrating that the death of a single star can resonate across thousands of light-years, shaping the composition, structure, and evolution of the galaxy for millions of years to come. Westerlund 1-26 is not just a scientific marvel, it's a star that inspires, or with its sheer scale and unusual characteristics, making it a treasure trove of interesting facts and cosmic trivia. One of the most mind-boggling facts is its size relative to our solar system. If Westerlund 1-26 were placed at the center of the Sun, its enormous envelope would extend past the orbit of Jupiter. That means Mercury, Venus, Earth, Mars, the asteroid belt, and even Jupiter itself would all be engulfed within the star's outer layers. Imagining the Sun as a tiny inside this colossal red supergiant helps convey the staggering proportions of the universe's giants in a way that is almost beyond human intuition. Another remarkable fact about Westerlund 1-26 is its variability. Like many red supergiants, it exhibits fluctuations in brightness due to pulsations in its outer layers. These pulsations are caused by the unstable balance between gravity and radiation in the star's enormous, diffuse envelope. Over time, these variations provide astronomers with critical clues about the star's internal structure, mass loss rate, and evolutionary stage. The fact that a star of this size can breathe in such a way adds an almost poetic dimension to the study of stellar physics. Westerlund 1-26 is also notable for its extreme mass loss behavior. The star is shedding material at prodigious rates through stellar winds, forming complex nebulae around it. Some of these ejected materials may eventually coalesce to form new stars or contribute to the interstellar medium, meaning that the star is actively shaping its cosmic environment even before it reaches its final supernova stage. In effect, Westerlund 1-26 is both a destroyer and creator, illustrating the cyclical nature of matter in the galaxy. The star's environment adds another layer of fascination. It resides in the dense Westerlund 1 cluster, surrounded by dozens of other massive and evolved stars. These neighbors create a dynamic, high-energy environment, with strong radiation fields, colliding stellar winds, and potential gravitational interactions. Westerlund 1-26, as one of the largest members, dominates its neighborhood, making it a central figure in one of the most extreme star clusters in the Milky Way. Finally, Westerlund 1-26's infrared visibility is a unique feature that underscores its obscured location in the galaxy. While hidden from optical telescopes due to interstellar dust, the star shines brightly in infrared, allowing astronomers to peer through the cosmic veil and study its properties. This combination of immense size, extraordinary luminosity, and hidden presence in a dust-obscured cluster gives Westerlund 1-26 a kind of cosmic mystique, making it one of the most intriguing objects in the Milky Way. In short, Westerlund 1-26 is a cosmic giant with almost unbelievable dimensions, extreme behaviors, and a dramatic role in its stellar neighborhood. Facts like its ability to fit the orbit of Jupiter inside it not only illustrate its size but also serve as a vivid reminder of the extremes that nature can produce, expanding our sense of scale and the diversity of stars in the universe. Westerlund 1-26 holds a position of critical importance in astrophysics because it provides an unparalleled laboratory for studying extreme stellar evolution. Stars of this size and mass are rare, and observing them allows scientists to investigate processes that cannot be replicated in laboratories on Earth. By studying Westerlund 1-26, astronomers gain insights into the life cycles of massive stars, the mechanisms that drive their enormous luminosities, and the physical processes responsible for the late stages of stellar evolution. It serves as a real-world example of how stars behave when pushed to the extremes of size, mass, and energy output. One of the primary areas of interest is mass loss rates. Red supergiants like Westerlund 1-26 shed enormous amounts of material through stellar winds and episodic eruptions. Quantifying these mass loss rates is crucial for understanding how massive stars evolve and how they prepare for their ultimate fate as supernovae. Accurate measurements of mass loss inform theoretical models, influencing predictions about a star's lifespan, the size and composition of its envelope, and the timing and nature of its eventual explosion. Without observational data from extreme examples like Westerlund 1-26, models of stellar evolution remain incomplete or uncertain. Astronomers also study Westerlund 1-26 as a supernova progenitor. Massive red supergiants are among the primary candidates for Type II supernovae, and observing stars in this stage helps scientists predict the characteristics of these explosive events. By measuring the star's mass, luminosity, radius, and chemical composition, researchers can estimate the type of remnant it will leave behind, whether a neutron star or black hole, and better understand the nucleosynthesis of heavy elements during supernova explosions. In other words, Westerlund 1-26 provides a preview of a supernova in the making, allowing astronomers to test their theories against a real-world example. Another key reason for its scientific importance is the extreme physics it exhibits. The star's enormous radius, high luminosity, relatively cool surface temperature, and turbulent envelope all challenge existing models of stellar structure. Studying how energy is transported through such an enormous and diffuse outer layer, how pulsations affect mass loss, and how the star interacts with its dense cluster environment helps refine theoretical frameworks for massive star evolution. Observations of Westerlund 1-26 allow astronomers to calibrate models of stellar atmospheres, convective processes, and radiative transfer under conditions that are unattainable in smaller or more ordinary stars. Additionally, Westerlund 1-26 provides a window into cluster dynamics and population studies. As a member of the Westerlund 1 cluster, it exists among dozens of other massive, evolved stars. Comparing its properties to neighboring stars allows researchers to explore how initial mass, environment, and interactions influence the evolution of massive stars. This comparative approach is essential for understanding stellar populations, the evolution of massive clusters, and the broader chemical and dynamical evolution of the galaxy. Finally, the stars study has implications beyond astrophysics. By understanding extreme stellar processes, astronomers gain insight into the origin of elements essential for planets and life, the physics of supernovae that shape galaxies, and the formation of exotic objects like neutron stars and black holes. Westerlund 1-26 is not just a subject of curiosity. It is a cosmic laboratory, a benchmark against which theories of massive star behavior are tested, refined, and sometimes challenged. In summary, Westerlund 1-26 is scientifically important because it provides a unique opportunity to study massive stellar evolution, extreme mass loss processes, and supernova progenitors. Observations of this star help answer fundamental questions about how massive stars live, die, and influence the cosmos, bridging the gap between theoretical models and the extreme realities of the universe. Stars like Westerlund 1-26 push the boundaries of theoretical astrophysics, presenting challenges that force scientists to refine or even rethink models of stellar physics. One of the central difficulties arises from the star's enormous size and low-density envelope. Most stellar evolution models are calibrated on smaller, well-understood stars, like the Sun or slightly more massive main-sequence stars. When a star swells to thousands of times the Sun's radius, its outer layers behave in ways that are difficult to simulate. Convection becomes extreme, with giant bubbles of gas moving across vast distances. Radiation pressure interacts with turbulent flows in unpredictable ways, and the tenuous envelope is prone to instabilities that can trigger massive ejections of material. Incorporating all of these phenomena into a single, accurate model is a major computational and theoretical challenge. Another complication comes from mass loss processes. Westerlund 1-26 is shedding enormous amounts of material via stellar winds and episodic eruptions. Predicting the rates, velocities, and composition of this mass loss requires a detailed understanding of radiation pressure, convection, pulsation, and magnetic effects, all of which are difficult to model accurately in stars with such extreme parameters. Small errors in assumptions about mass loss can dramatically change predictions of the star's remaining lifetime, luminosity, and the nature of its eventual supernova, highlighting the sensitivity of stellar models to these uncertain processes. The interaction between the core and the envelope also challenges theoretical models. In massive red supergiants, energy generated in the dense, hot core must be transported through a hugely extended, relatively cool envelope. This transport occurs via radiation and convection, but in such an enormous star, these processes are not uniform. Surface pulsations, temperature gradients, and convective instabilities all create a complex, dynamic system that is extremely difficult to capture in one-dimensional or even three-dimensional models. Simulations must account for both global and local effects, a requirement that significantly increases computational complexity and uncertainty. Westerlund 1-26 also challenges models because of cluster effects and environmental interactions. The star is part of the dense Westerlund 1 cluster, where nearby massive stars produce intense radiation fields, strong stellar winds, and gravitational interactions. These external influences can affect mass loss, envelope dynamics, and even angular momentum evolution, adding further layers of complexity that are difficult to isolate and incorporate into theoretical calculations. Unlike isolated stars, cluster members like Westerlund 1-26 cannot be fully understood without considering these environmental factors. Finally, the end stages of evolution for stars like Westerlund 1-26 are especially uncertain. Predicting exactly when the core will collapse, how the outer envelope will respond, and what type of supernova or remnant will result requires precise knowledge of the star's internal structure, rotation, magnetic fields, and prior mass loss. Even small uncertainties in these parameters can lead to dramatically different outcomes, ranging from the formation of a neutron star to a black hole, or variations in supernova luminosity and ejecta composition. In this sense, Westerlund 1-26 is a stress test for stellar evolution theory, exposing the limits of current models and driving astronomers to develop more sophisticated simulations. In summary, stars like Westerlund 1-26 challenge our understanding of stellar physics because of their extreme size, complex mass loss processes, dynamic envelopes, and interactions with their environments. They push the limits of computational modeling, requiring a combination of observational data, theoretical physics, and numerical simulation to accurately describe their behavior. Studying such stars not only improves our understanding of red supergiants but also advances the broader field of astrophysics, as these extreme cases illuminate phenomena that more ordinary stars cannot reveal. Westerlund 1-26 is more than just a star. It is a cosmic monument to the extremes of nature, a celestial titan whose sheer scale and energy challenge our imagination. Picture its gargantuan radius, stretching beyond the orbit of Jupiter, its surface a cool, deep red glow radiating hundreds of thousands of times the sun's luminosity. Visualize its tenuous outer layers being pushed outward by convective forces and stellar winds, creating vast nebulae of gas and dust that enrich the galaxy. Envision it as part of the densely packed Westerlund 1 cluster, surrounded by other massive stars, all interacting in a dynamic dance of energy, gravity, and radiation. These awe-inspiring visuals remind us that the universe is not static or uniform but a living, breathing expanse of extremes. Westerlund 1-26 also serves as a reminder of cosmic time and scale. Though it has existed for only a few million years, a fleeting lifespan compared to the Sun, its life and death will have repercussions across thousands of light-years. When it finally explodes as a supernova, the event will scatter heavy elements across its galactic neighborhood, influencing the formation of future stars and planets, and leaving behind a neutron star or black hole as a lasting testament to its existence. In this way, the life of one star is intimately connected to the broader story of the galaxy, illustrating how individual celestial objects can shape the cosmos in profound ways. From a scientific perspective, Westerlund 1-26 represents both opportunity and challenge. Its extreme size, luminosity, and mass loss behavior push the boundaries of stellar physics, testing models of evolution and providing insights into supernova progenitors. Its study helps astronomers understand not only how massive stars live and die, but also how galaxies evolve chemically and dynamically over time. Each observation, each data point, peels back another layer of understanding about the life cycles of the universe's most colossal stars. Beyond science, there is a more philosophical takeaway. Contemplating Westerlund 1-26 inspires awe, humility, and imagination. It invites us to visualize the unimaginable, to grasp the scales that dwarf human experience, and to ponder the extraordinary diversity of the universe. Consider a star so immense that our entire inner solar system would fit inside it. Imagine it shining with a brilliance that outshines hundreds of thousands of suns, its outer layers flowing outward in a cosmic wind, sculpting its neighborhood and preparing for a supernova that will ripple across light years. These mental images help bridge the gap between abstract numbers and true cosmic wonder. In the end, Westerlund 1-26 is a symbol of the extremes of existence, a testament to nature's power, a laboratory for understanding the universe, and a reminder that the cosmos contains wonders far beyond human scale. Its story, from formation to red supergiant, from mass loss to impending supernova, is a vivid illustration of the life cycle of massive stars. By studying and imagining such giants, we gain perspective on our place in the universe, the forces that shape galaxies, and the extraordinary diversity of stellar life. As viewers reflect on Westerlund 1-26, it is worth holding on to this thought: the universe is vast, dynamic, and full of giants, both in scale and in impact. Stars like Westerlund 1-26 are not distant abstractions. They are living, evolving entities, shaping their surroundings, enriching the cosmos, and reminding us that the universe is far bigger, more energetic, and more awe-inspiring than we can fully comprehend. Let these images, numbers, and stories inspire curiosity, imagination, and wonder at the vast, dynamic, and beautiful universe we are a part of. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.